Beneath every train's thunder lies a hidden revolution, the rails themselves shaping 200 years of progress in silence. Before high-speed steel streaked across continents, miners in the 12th century carved wooden runways underground, inventing the very path trains still follow. Every mile of track changed the fate of nations and the fabric of industry, yet most have forgotten this foundation. Why did a simple plank of wood set off an endless race of invention, conflict, and triumph? Welcome to Rails Through Time. The untold story begins where light disappears and guidance is born. Deep beneath the green hills of northern Germany, flickering candlelight reveals a world shaped by sweat and timber. In the tunnels of Rammelsberg, miners carve out a living in darkness, their hands rough from lifting oak planks and hammering them into thick mud. Water drips from the ceiling, pooling around their boots, but the work never stops. Each day, these men lay down wooden rails, simple beams, sometimes no wider than a man's hand, fastened with pegs they call trenels. The rails guide heavy carts loaded with ore, keeping their wheels from sinking into the mire. It's a small invention, born from necessity, but it changes everything. Now, a single miner can move a cart that once took 3 men to drag. The rails wear quickly, splitting or sinking, and must be checked and set right at every shift. Yet, the miners persist, shaping and joining the planks by lantern light, adjusting each board by touch and instinct. Their tools are few, an adze, a mallet, a handful of iron spikes. But with each repair, each guided cart, they build something lasting, a path through darkness, and the first principle of every railway to come: guidance, cut from wood and will. Above ground, the idea takes hold in a new world of open sky and rolling English fields. By 1604, teams of laborers in Nottinghamshire lay the first surface wagonway at Walleton, guiding heavy coal wagons along timber rails. Horses, harnessed and steady, pull loads that once demanded entire crews, their hooves striking gravel as cartwheels follow the wooden path. The work is relentless. Joiners and blacksmiths measure, cut, and fit planks, shaping each rail to withstand the weight of commerce. Coal hauliers, faces dark with dust, test the rails every morning, feeling for loose boards or warped timbers. When the rails splinter or sag, they patch them with new wood, or when coin allows, cap the tops with iron. These iron-topped planks, first tried in the northern coal fields, last longer under the grind of wheels and hooves. Each repair, each length of track, pushes coal farther from pit to port. As the network spreads, the rhythm of hammer and hoof echoes across the countryside, a quiet revolution, driven not by invention alone, but by the daily demands of trade and the hands that build the way. At the dawn of the industrial age, a new contest played out not in boardrooms, but in the blackened workshops of Britain. John Kerr, a colliery manager in Sheffield, shaped cast iron into L-shaped plates in 1787. His design guided flat wagon wheels along a raised lip, making it easy to build carts, but trapping stones, mud, and ice in the groove. When debris clogged the channel, wagons lurched to a halt, sometimes flinging loads and men alike into the ditch. Nearby, William Jessop eyed the problem from a different angle. In 1789, Jessop rolled out the edge rail, a rounded bar where the guiding flange was moved from the rail to the wheel itself. Now, as a flanged wheel hugged the rail's edge, grit and gravel fell harmlessly away. On the Nanpantan tram road, carts glided forward, their wheels locked to the path but free from jams. The debate between plateway and edge rail wasn't just about metal shapes. It was a battle of ideas, each inventor convinced that form alone could tame the chaos of early railways. Their rivalry set the first standards for what a railway could be, and every rail since has carried the mark of this early engineering duel. The first steam locomotive to run on rails, Trevithick's Penny Darren engine, thundered down the tramroad in 1804 and left a trail of broken cast iron in its wake. The weight and force of steam shattered rails that had held up under horses and wagons, splintering them with sharp echoing cracks. Workers scrambled to patch the track by lantern light, dragging in spare lengths and hammering makeshift repairs through the night. Reports from the line described wagons teetering on fractured rails, men risking injury to keep the cargo moving. Every break threatened contracts and safety, and the promise of steam seemed on the brink of collapse. In 1820, John Birkinshaw at Bedlington Iron Works offered a way out. He rolled wrought iron into rails 15 feet long, 5 times the length of brittle cast iron. These new rails flexed under heavy loads, bending but refusing to snap. Birkinshaw wrote to investors with urgency, promising rails that could outlast storms and steam alike. Field tests drew crowds. Laborers swung hammers at the rails, but the metal bowed and sprang back, unbroken. When the Stockton and Darlington Railway opened in 1825, 12 miles of Bedlington's rails carried the world's first public steam trains safely forward. For the first time, the path beneath the wheels was as resilient as the engines above, a silent triumph of strength and ingenuity. In the furnace-lit workshops of mid-19th century England, molten steel poured in rivers of orange and white, casting new hope on the rails below. Henry Bessemer's invention, his converter roaring with forced air, could turn pig iron into steel faster than any process before. Yet the first steel rails were brittle, snapping under the weight of passing trains. The missing secret lay with Robert Forrester Mouchet, a quiet metallurgist who studied the chemistry of the metal itself. By adding Spiegeleisen, a special alloy rich in manganese, Mouchet gave Bessemer's steel both strength and resilience. In 1857, Derby Station became the proving ground. Mouchet's rails were laid, gleaming in the morning light, and for 16 years they endured the pounding of locomotives and freight, showing almost no wear while iron rails nearby had to be replaced again and again. The numbers told the story. Where iron rails lasted just a few years, steel promised decades of service. Railways across Britain took notice. Orders for steel rails soared, and by the end of the century, steel had become the backbone of global rail travel. Every mile of track now carried not just the weight of trains, but the proof of a metallurgical leap, one forged by fire, refined by science, and tested by time. 2 visions, 2 men, and a nation divided by the width of a rail. George Stephenson, the practical engineer from Northumberland, built his railways to a gauge of 4 feet 8.5 inches, a measurement rooted in the coal fields of the north, proven by years of steady traffic. Isambard Kingdom Brunel, bold and ambitious, saw a future for the Great Western Railway on a broad gauge of 7 feet, promising smoother rides and higher speeds. For a decade, British railways grew in both directions, each new company forced to choose a side. At stations where the two systems met, chaos reigned. Passengers hauled their luggage across platforms, goods were unloaded and reloaded, and every transfer meant wasted hours and lost profit. Parliamentary committees filled with heated arguments. Stephenson argued for unity. Let no rail stand alone. Brunel countered. Wider means swifter, broader means truer. But the network could not endure the break. In 1846, Parliament passed the Gauge Act, declaring Stephenson's gauge the standard for all new lines. The broad gauge lingered in pockets, but the age of fractured rails was over. Britain's iron arteries, at last, began to flow as one. Beneath every rail lies an unseen world, layers shaped by centuries of trial and invention. The sleeper, or tie, runs crosswise under the steel, holding each rail to its perfect width. In the earliest days, these were rough-hewn beams of oak or pine, cut by hand and set into gravel or earth. Timber offered resilience, absorbing the shock of passing wheels, but rotted quickly in damp ground. Crews worked year-round, replacing sleepers and tamping them tight, their labor as constant as the trains above. Over time, engineers turned to creosote, soaking the wood in dark preservative to fight decay. Yet even treated timber had limits. Steel sleepers arrived in the mid-20th century, strong but prone to rust and complex to fit. The greatest leap came with pre-stressed concrete. Now each sleeper weighs as much as a man, spreading the weight of locomotives across a bed of crushed stone. This ballast, broken granite or limestone, does more than cushion the track. It drains rain, holds sleepers steady, and keeps rails true through heat, frost, and flood. Every fastening, from iron spike to modern clip, binds the system together. Plate layers, those who walk the line, test each joint, listening for the hollow ring of a loose tie or the crunch of fouled ballast. Their work is quiet, careful, and essential. Without these hidden layers, steel would twist and sink, and every journey would come to a halt. On today's railways, the work beneath the trains is guided by data as much as by muscle. Continuous welded rail, an unbroken ribbon of steel, hundreds of meters long, has replaced the patchwork of joints and bolts. The old rhythm of clattering wheels has faded, replaced by a smooth, silent glide. But with that silence comes a new challenge. Steel expands and contracts with every change in temperature, storing enormous forces inside each rail. Crews monitor these stresses with precision, using sensors to keep the neutral temperature within a safe range. When the summer sun pushes the steel past its limits, teams respond with calculated adjustments, preventing the sudden buckling known as a sun kink. Modern inspection teams now rely on ultrasonic scanners to peer inside the rails, searching for cracks invisible to the eye. Automated vehicles sweep along at 40 kilometers per hour, picking up flaws as small as a grain of rice. Overhead, drones equipped with AI scan the track for damage, relaying images and data in real time. Canadian National Railway's adoption of drone and AI inspections has cut unscheduled downtime by 40%, allowing crews to fix problems before they become disasters. Every day, engineers balance tradition and technology, ensuring that the rails beneath us remain as strong and reliable as ever, an unbroken line of innovation stretching from the age of timber to the digital frontier. In 1857, steel rails laid at Derby remained in service for over 16 years, setting a new standard for railway durability. This documentary has traced how wooden planks in 12th century German mines became the steel and concrete tracks supporting high-speed trains today. Every major advance, from John Birkinshaw's wrought iron rails to the Bessemer process and the Gauge Act of 1846, is documented in engineering records and parliamentary archives. Yet the daily work of early miners and many technical details of ancient track construction remain only partially understood, as surviving records are incomplete. Today, continuous welded rails and real-time digital inspections have cut downtime by up to 40%, according to CN Rail's published results. The facts show that progress came from solving each material crisis and standardizing every layer beneath the train. Our civilization's movement depends on the rails, whose silent evolution is recorded in every mile of track. The story of railroads is not just above ground, but in the foundations below, built by centuries of invention, endurance, and vigilance.